Welcome back. The last step in our generation is to place the player and the enemies around our dungeon so that we can actually have some gameplay going on. The important part in this step is that we have our path that the player can always reach. So those are the tiles representing the path. So the enemies needs to be placed in such way that they are placed near the path or in a way that they can reach the path to encounter the player or the player to encounter those enemies. Now there are spaces in our dungeon like this space here where the tiles are simply blocked by all the props around those tiles. This means that if we place the enemies here, they will not be able to reach the player and the player will not be able to reach them if those props are non-destructible. This is why we are going to use breadth first search algorithm to find all the tiles that are reachable from our path in our room to avoid placing the enemies in the spaces where they cannot really encounter the player and cannot really add value to our gameplay. I have already shown you this green gizmo painting the tiles which can serve as a placement positions for our enemies, and as you can see this part is excluded, as well as the positions where we have already placed our props. And as you can see, those enemies that were placed by our algorithm are all placed on one of the tiles that are inside this green area. And I do this for all of the rooms to avoid placement of the enemies in those points. And of course we have a player room where there is only the player. In our project we had this prop placer script that had this onFinish event, and it calls the agent placer game object that has the agent placer script on it, and it calls the place agents method, and we are going to place the enemies and the player, and we have some additional variables here that I'll explain. So let me show you the code behind this script. This is a very simple script that will have the reference to the enemy prefab and the player prefab. Obviously we are only using one type of enemy, but you could add more to this and extend this script. Now next, after we have those game objects references, we're going to have a private int player room index based on the dungeon rooms that we have generated in our simple dungeon generator. I have added those rooms to the list, and I have added the first room, which is the middle room, and the ones on the edges. So I am setting the agent to be placed in one of those edge rooms that are only reaching the center room. I will have the Cinemachine virtual camera reference so that I can point my camera to look at the player when I spawn. Next we have a list of int room enemies count, where I can add a specific count of enemies to each room based on the index. Index 0 will represent the room that we have created first in our dungeon. Next we have our dungeon data reference, and we have some gizmos. This is a bullflag show gizmo. And we have this place agents method. Again, if we do not have any data, we do not need to bother with the rest of the code because we need some data from this dungeon data object. So the logic is pretty simple. For I till I rooms count, we are going to take each room, and to place the enemies we need to analyze each room and create kind of the map of the reachable positions from the path. And this is where our room graph class will come in and will allow us to run breadth first search algorithm on those rooms. Let me show it to you. The room graph will contain a 4 directions list. This is a similar list that we had previously. We're going to have a graph represented as the dictionary of vector to int and a list of vector to ints. I will explain it soon. The room graph constructor will take in room floor and will convert this into our dictionary. So for each position in our room floor, we are going to generate a list of neighbors, and we are going to loop for each direction in 4 directions, and we are going to calculate a temp position of a neighbor that can be in our room floor hash set, and we are going to check if it is, then we are going to add it to the neighbors, and to our graph, which is a dictionary, we are going to add the position of the tile as well as the list of its neighbors if they exist. And this is how we are going to create a graph that we will later use in a breadth first search algorithm. Okay, for now let's get back to the place agents method. So we have our room graph without any knowledge about the room yet. And next we are going to find a path inside the room so that we can select one of those positions to have as a starting point for our algorithm. So we create hashset room floor equals new hashset room floor tiles. And again, we are using the hashset type of the collections because it contains this intersect with method, which allows us to intersect the room floor. So this is this hashset with the dungeon data.path. So the vector to ints, so the tiles representing our path, creating as the part of the room that is the floor. So for the center room, it will be those tiles. So we have only those tiles that represent the path inside this one room. Okay, so why did we do this? Well, we need to have the start position to run our breadth first search algorithm. So basically, we are going to below use this room floor that is no longer the room floor, but only the room floor that represents the path. And we are going to create our dictionary, so our room map, so vector 2 and vector 2. Room map equals room graph, run breadth first search algorithm, taking room floor, so our hashset. First, we are going to use the link library to get the first value from our hashset because hashset does not include any indices of its content. So we are using this method and we are going to pass to it occupied nodes, so the prop positions, and those will not be accessible to walk on by our enemies. Let me show you the breadth first search algorithm, although this is a very common implementation. So we are going to return a dictionary of vector 2 and vector 2. Now this is a map that could be used as a path from a specific position to reach another position, but we are not going to use it like this. We are only interested in the positions found by this map. So to run a breadth first search, we are going to create a queue collection that we will take in vector to ints, and we are going to then queue the start position. We are going to also have a hash set of vector to int visited nodes, and we are going to add again the start position. Having this, we are going to create our map, so the dictionary of vector to int map, and we are going to add to our map the start position. So this map isn't that important. What is important for us is those keys of the dictionary, because those represent all the positions that can be reached starting at the start position. So we are going to add the start position to our map, and we are going to have this queue with one node start position. In the while loop, we are going to loop while the nodes to visit queue has any new positions. If it has, right now it has one at the start, we are going to dequeue this, removing the start position from our queue, and we are going to get the list of neighbors using our graph. Now we have created our graph when we have created the room graph representation of our room, and this has automatically found all the neighbors of each tile in our room. If we have this, we can run any type of pathfinding on our room graph representation. Right now, all we need to do is loop for each vector to int neighbor position in our neighbors of this start tile, so this tile on the path inside the room, and we are going to simply check if the neighbor position, so if visited node contains the neighbor position, equals false, and the occupied nodes contains the neighbor positions equals false. So this means that our enemy potentially could stand on it and still reach our start position. We are going to add this neighbor position to our nodes to visit and queue. We are going to add this to our visited nodes hash set, the neighbor position, and we are going to add it to our map. And we are going to keep on looping through each of the neighbor and the neighbors of the neighbors until we reach or until we visit all the tiles representing our room, and we are going to return our dictionary, so our map, as the return value of this breadth first search algorithm. What we are going to achieve with this is that now we have our room map, and the room positions accessible from the path will be equal to the room map dot keys, so the keys of our dictionary representing our room map. Now here we are going to order them by the GUI ID, new GUI ID, so basically we are going to shuffle them because it will make a placement of our enemies a bit more organic. Now if we have those positions, then we are going to check if room enemies count, so our list of the quantity of enemies contains some values. basically we want to place the enemies in our room and with this quantity, so room enemy count with the index I. So place enemies method, let me go to the definition of it. All it will do is loop for each k equals 0, k less than enemy count k plus plus. We're going to access room, positions accessible from the path count. If this is less than k, we're going to return, because if we want to place 100 enemies but we only have 50 tiles, then we are going to simply return. But if it is not the case, we are going to create a new game object instantiating the enemy prefab. We are going to set its local position to be the position accessible from path with index k plus vector2 1.1 times point half, so that we place the enemy in the center of our tile, and we are going to add room enemies in the room, add the enemy game object reference for the sake of being able to quickly destroy it if we want to regenerate our room. Okay, so let's go back to our main logic. We have placed the enemies inside our room, and in case we have reached the room that the player should be placed in, we are going to check. We are going to actually run similar logic. We are going to instantiate the player. We are going to set the local position of the player object to be the room center position plus vector 2.1 times 0.5, so that we place the player in the center of the tile. And all we need to do additionally is to make the virtual camera look at and follow the player. And we are going to add to the dungeon data player reference equals the player. And this is it. I do not have any more steps in my procedural generation. So from the beginning, first we are going to generate the dungeon layout, then we are going to place the props, then we place the enemies in the spaces near the path, or the places from which we can reach the path. As you can see, this whole area was separated by our obstacles. And lastly, we are going to focus the camera on the player, so that now we can walk around our dungeon and fight the enemies. And again, sometimes, as you can see, this we can walk near those obstacles to reach this position here, this area, because we have modified our collider to be 0.8 of the size of the sprite. But basically, in those cases, you might want to run additional checks to see if majority of your tiles of your dungeon are accessible or not. If not, then try regenerating your room. But as you can see, the end result looks pretty decent, and we have our enemies. They are trying to reach me because they can the collider allows them to see me using a raycast, and here I have died. But basically we have our dungeon generated. Okay, and this is it for this tutorial. I hope that you have enjoyed this tutorial. If you did, leave a like, leave a comment, and remember, you can download the full project from my Patreon. The link will be in the description. Thanks a lot for watching. See you in the next tutorial.